It goes into the PowerPoint.
All right, so let's start out. It seems strange to be starting the class in this room.
Yeah.
So let's start with, are there any questions before we talk about the lab? Yes, Chance?
Okay, so on the master set 4, on the first question, part B, when it's talking about it being released, I'm not understanding how we're supposed to find, like, what the initial velocity needs to be for it to hit the thing if there's no time associated.
Find the time. By the time you get to part B, you know how far over and how far up it needs to go.
Yes.
So you have, we'll just call this R and H. So for the horizontal, let's set up our coordinate system like this. So we got our I hat and J hat, displacement, initial velocity, final velocity, acceleration, and time. Same is taking place on Earth. So all the acceleration is vertical and downwards.
Yeah.
So negative 9.8 meters per second squared, and it's negative because I say up is positive. This is 0 meters per second squared. This is H and R. And we know, now I know it is being launched at some angle. I don't know what the speed is, but I know the angle.
Yes, I have the angle.
All right, so if I call that angle theta, this becomes V cosine theta and V sine theta. So you know H, you know R, you don't know V, and V, pretty much V and time are two unknowns. So if you put it into the cake equation, the displacement is equal to VIT plus 1/2 AT squared. You plug the horizontal stuff in, you plug the vertical stuff in, and you'll have two equations, two unknowns. You won't know V and you don't know T. And it's solvable at that point.
It is solvable?
Two equations, two unknowns. They are independent of each other, so therefore,
So I would set them, find a way to set them equal to each other?
well, for the horizontal equation, this second term drops out because acceleration is 0. So you're left with some number is equal to V cosine theta t. If you solve for VT here,
Okay.
and then plug that into the second equation for VT, then you'll have just an equation with time in it and solve.
Okay. Alright, thank you. That makes more sense, 'cause that was, I was getting confused.
There is a certain point in physics when you just have to have blind faith that I'm going to plug into the equations I know that I have to use and hope that there's a way to solve it.
Oh, for some reason I thought you had said that we weren't supposed to use those equations, but I guess I was thinking something else.
Maybe I just told you, just wanted to mess with your head.
He's going to make my life difficult, yeah.
I'm not sure what I said to make you think that.
No,
but-
I think I misinterpreted something, so, but thank you.
Any other questions right now? All right, to let you know that, was that a hand up over there? No, okay. That there's some past assignments I'm gonna hand back today that, the ones that were done on paper, I made sure I got those done first. So I'm gonna be handing back the first lab and the linear motion lab and master set 2. Those that were done on paper, those will be handed back. The electronic ones for the linear motion lab, I'm almost done with those, so those should be done by the end of today, so those will be posted, the electronic versions. But since this is the last chance we meet before the test, that we meet face-to-face, where I can hand stuff back, I want to make sure I get at least that back to you. The grade that's on the linear motion lab at the top, that's the minimum. It probably will be the final grade, but it might change once I have all the grades in, but it won't be less than what's written at the top of your page. All right, so let's talk a little bit about today's lab.
Is there a pile for the projectile for the one for today yet?
When you put it down, there will be.
I'm just,
There's now a pile. All right. A tiny little board like this, I feel like a gym coach. All right, so this lab is a little bit different than the classic Newton's Law lab, just because I wanted something different. So for the first part, we are, let's see, this first part, mass is constant. We're basically checking to see if F equals MA. Mass is constant, and for the second part, so that's, I think, part A, may I see your version of it? Make sure I didn't put some, yeah. A, constant mass, B, constant force. So if mass is constant, acceleration and force should be directly proportional. If the force is constant, mass and acceleration should be inversely proportional. So for the first part, you're going to be changing the force. So this is our independent variable. Acceleration will depend on it by changing the angle. So we're going to be changing the angle of one of the tracks down there. Now, at the low angles, doing it on top of the table should not be a problem. But when you get to around 40 degrees or so, when you get to the steeper angles, it gets a lot more difficult. Now, we don't have carpet in here so for the end of the track to dig into it, so feel free to move the mat if you need to make life a little bit simpler. But if the track gets off, please make sure that you put it back to the correct angle. And one of the indications that the angle is off is suddenly that the indicator of acceleration suddenly changes. Now, as it goes down, you're going to have the sensor up here, and it's going to measure the position of the cart. It's going to come up with a bunch of data points. And what you probably are going to see as you're holding it is that if you did looking at the graph mode, you're going to get somewhat of a straight line, and then it will go like this, and then it's going to hit the end. If you're holding it too close to the sensor, then what you would see more likely is it'll be straight like this, and then there's a sharp point right there. That's supposed to be a sharp point. It's more of a sharp point than a gradual. Either way, in this version of the lab, you want to pick a point, you want to pick a region that the cart is clearly moving down the track. So don't do a curve fit of all of that, because this includes before you let go. Don't include this part over here, because that's after it hits something. We want it while it's moving down the track. And so make sure you pick that right spot. You do a curve fit, and it'll show you y equals ax squared plus bx plus c, and then a equals b equals c equals, and then RMSE. This right here is not the acceleration. And that is probably one of the biggest mistakes I see, is that people saying that's the acceleration. That is half of the acceleration. The LabQuest is not smart enough to realize that we're dealing with time here, even though you tell it, I want this axis to be time, it still says x. What you're plugging into, or what it's telling you, is my position is equal to 1/2 at squared plus vit plus my initial position.
oh,
That's basically final position. So the coefficient of the quadratic term here is half the acceleration. So the first part, I think, is relatively straightforward. Mass is the same. You have the cart. I believe you have the load mass on it. The load masses are the black bars, and I believe it is marked load mass. It's something clever like that. We have two type carts here, plunger carts and the collision carts. If you grab a plunger cart, no problem with that, just make sure that the plunger is not pointed towards the sensor. Sensor's usually pretty good about ignoring the plunger, but just in case, if the plunger is pointed towards the sensor, push the plunger in and lock it into place. When you put them back, please put them back in the right box. Load masses, that's why I walked over here. You see them? They might be in the other room.
I see hook masses.
Yeah. Oh, here we go. Short, long load masses. The long load mass. The short is about half the length of the long. If you need to mark on them, some people already did, they put tape on it, there's the number 1 right there, I have no problem with that. Yeah, they put a little, let's say Scotch tape, what's the,
Like
Cellophane
elastic
tape
tape
or something, yeah.
they put cellophane tape on it and wrote on it, I'm fine with that. Preferably, you'll put the tape, if you're using tape and I'm writing on the tape, do that before you find the mass. Now, the second part, flashing back, a couple years ago, I had a group, they went through the first part, they're working on the second part. About an hour and a half into it, I realized they're doing the second part completely wrong. And they had to redo it. The second part, you are giving a constant force. So what you're gonna do is, you're gonna start out at, I think it's a 40-degree angle, whatever's prescribed in there. Let's see if this works.
Yeah, 40 degrees.
You got the cart on there with nothing on it, and you do pretty much the exact same thing that you just did. Before you let it run, or just after you let it run, you get the force sensor, and the force sensor, you figure out how much force is required to keep the cart from going down the track. That should equal the amount of force that is exerted on the cart down the track. So if it's in equilibrium, the force down the track should equal the force pushing it up the track. So you put it on there, then you take it off. Please don't put it at the bottom of it for this cart to run into. This is for finding the force that the cart exerts when it's in static equilibrium. So you take this off, you run the cart, you do however many trials, I think it's 4 trials or 5. Then when you add a mass, you change the angle so that the force is the same thing you got the first time, plus or minus some little margin there. So that is how the second part is done. So you'll do however many trials, like 4 trials or so at this angle, then it'll come down, then you'll move it down to the next angle. At some point, I'm going to write up on the board a very crude estimates of the values I would expect you to get for a couple things. So these are not written in stone. This is a crude estimate of what I would expect your values of A to be and of what these angles are.
Just like a question for peace of mind.
Yes?
How much trouble do people typically have with this lab? Like, just because I find myself stressed out when I'm doing these labs.
Once you get the hang of it, it's not bad. It's the first trial is the toughest one for each part.
Okay.
But there is a video posted if you have access to the internet, and if nothing else, we have it here on this computer. You can watch the video and or skip through it and see what I did. Anyway, I think, any questions? Then let us, of course, rejoice, because this is physics.
Man, do I love Newton's second law.
Who doesn't?